This is the second of 4 programs describing the operation and maintenance of an air brake system. We'll study this system and its components. But first, let's review the devices in Program 1, the air supply system. The compressor produces compressed air for the system. Air dryers prevent contaminants from entering the system. Proper system pressure is maintained by a governor connected to the compressor, air dryer, and supply reservoir. In the supply reservoir, a safety valve protects against overpressurization. 2 service reservoirs are protected by single check valves. And last, a low-pressure indicator switch and dash gauges track pressures. Now our service brake system discussion begins at the 2 service reservoirs. They form the basis or origination point for a dual or split service brake system. To take advantage of the separate reservoirs, a dual brake valve is needed. The dual brake, actually 2 separate valves in a single housing, is operated by a single treadle or pedal. Generally, all dual brake valves function the same way. Mounting methods may differ. This is the floor-mounted E6, and this, the firewall-mounted E7. We'll use the E6 to look at the major components of a dual brake valve. The actuation components of the E6, pedal or treadle, plunger, roller, stop button, boot, and fulcrum pin are interchangeable with other brake valves. The internal components are spring seat, graduating spring, primary piston, primary inlet and exhaust valves, secondary or relay piston, and secondary inlet and exhaust valves. Air from each reservoir enters its respective supply port on the brake valve. Because the circuits are normally closed, air does not pass through the valve until a brake application. The delivery ports are open to the exhaust at atmospheric pressure, shown in yellow. With a brake application, the treadle is depressed, and the plunger applies a force on the spring seat. This compresses the graduating spring, and in turn causes the primary piston to move. The primary piston, which incorporates the exhaust valve seat, closes the primary exhaust valve. As the exhaust valve closes, the primary inlet valve is moved off its seat, and air from the primary service reservoir flows out the primary delivery port. Air from the primary delivery passes through the bleed passage and enters the relay piston cavity. Primary delivery air pressure moves the relay piston, which incorporates the exhaust seat, and closes the secondary exhaust valve. After the secondary exhaust valve closes, the secondary inlet valve is moved off its seat, and secondary reservoir air flows out its delivery port. A balanced position in the primary circuit is achieved when the primary air pressure beneath the piston exerts a force equal to that of the driver's foot on the brake treadle. The primary piston moves slightly, closing the inlet, preventing further air delivery. In this position, the secondary circuit reaches a balanced position. Air pressure on the primary and secondary sides of the relay piston equalizes. As this balance is attained, the relay piston moves, closing the inlet and preventing further air delivery. When the treadle is fully depressed, as in a panic stop, both circuits are held open mechanically and full reservoir pressure is delivered. When the brake treadle is released, the mechanical force is removed from the spring seat, graduating spring, and primary piston. Air pressure and spring load move the primary piston. The exhaust opens and air pressure in the primary circuit goes out the exhaust port. As the air is exhausted from the primary side of the relay piston, air pressure and spring load move the relay piston, opening the secondary exhaust. If air pressure is lost in either circuit, the portion of the brake valve that still has air pressure supplied to it will continue to function. However, should air pressure be lost in the primary system, the relay piston will move by mechanical force from the driver's foot, not from air pressure delivery from the primary circuit. Here's a service tip. When only one circuit of the brake is supplied with air, the brake valve still functions. Remember this when troubleshooting for a no brakes or insufficient brakes complaint. Now let's see where the air from the brake valve goes. Vehicle manufacturers decide how the brake circuits are divided. The most commonly used is this front-rear axle split. The front axle service system is shown in red, the rear axle system in green. The primary circuit air pressure controls the service portion of the drive or rear axle spring brakes. The secondary circuit air pressure is delivered to the steering or front axle brake chambers. The chambers located at the wheels they serve convert compressed air energy into a mechanical force. This is the front axle brake chamber. In principle, it functions like a piston in a cylinder. The brake chamber has a pressure plate and a non-pressure plate with a rubber diaphragm between them. A channel-shaped clamp ring holds them together. The return spring in the chamber holds the push plate and rod assembly against the non-pressure side of the diaphragm. There are many sizes of brake chambers. Each develops a different mechanical force. A service brake chamber's size and relative power output is specified by a number representing the square inch area of its diaphragm. This chamber is a type 20. Its diaphragm has a 20 square inch area for air pressure to act on. With a brake application, air pressure enters the inlet port and acts upon the diaphragm. The diaphragm balloons and forces the push rod and push plate out of the chamber against the minimal resistance of the return spring. The brakes are thus applied. The force exerted against the push rod, and therefore the power of the brake application, is dependent upon the air pressure applied to the chamber diaphragm. If, for example, the brake delivered 30 psi pressure to a type 20 chamber, the push rod would move out with a force of 600 pounds. That's 30 psi on each of the diaphragm's 20 square inches, or 20 times 30. When the brake application is released, air in the brake chamber goes out the inlet port it entered. As air pressure is removed, the return spring retracts the push rod and releases the brakes. The standard service brake chamber just reviewed is used on the steering axle. Most vehicles are equipped with spring brake actuators on the rear or drive axles. The spring brake acts as an emergency and parking brake in addition to performing the service brake function on the rear axle. The operation of the parking and emergency brake function are discussed in another part of this series. For our purposes here, let's consider the spring brake as being the same as a standard brake chamber. The components in the service side of the spring brake look the same as those in a standard brake chamber, and they serve the same function during a service brake application. Threaded on the end of the push rod is a yoke assembly for attaching the slack adjuster. The slack adjuster is the final link between the air system and the cam brake in the wheel. It multiplies and transforms the linear force developed by the brake chamber into a rotational force, or torque, used to apply the foundation brake. Slack adjusters have designations indicating the torque they are expected to tolerate. A Type 20, for example, can withstand 20,000 inch-pounds of torque. The slack adjuster also provides a means for adjusting for brake lining wear. Manual slack adjusters are currently the most popular, but they require periodic manual brake adjustment. So automatic slack adjusters like this Bendix ASA 5 Sure Stroke are available as standard on some vehicles, as an option on most. The automatic adjustment provided by the ASA 5 yields consistent brake lining to drum clearance and brake actuator stroke. Brake performance is improved, maintenance reduced. When the brakes are applied, the brake actuator's push rod causes the slack adjuster to rotate the brake camshaft, which begins to force the brake shoes into contact with the drum. As the slack adjuster rotates, the yoke assembly pivots on the yoke pin, causing the adjusting link to be pulled upward. The travel of the adjusting link actuates the internal adjusting mechanism. This adjusts the brakes before the shoes contact the drum. All adjustment ceases when the shoes contact the drum. That's important. The ASA 5 senses or adjusts to a running shoe-to-drum clearance, not a brake chamber stroke. Over and under adjustments are therefore less likely. When the brake application is released, the actuator push rod returns to the released position. The camshaft rotates in the opposite direction to its new adjusted position, and the brakes are released. Here's another service tip. Lubricate the ASA 5 every 3 months or 25,000 miles, whichever comes first, and check proper operation every time you lube it. Make a service brake application and note the length of the brake actuator push rod stroke. If too long, there could be a problem with the ASA 5 or the foundation brake itself. The system discussed so far will stop the vehicle, but additional equipment will improve performance and safety. When the brakes are released, the air pressure from the pressure side of the chamber goes back through the exhaust port of the brake valve. As airline lengths increase, air travel time to and from the brake chamber increases. Worse still, as air pressure decreases, air travel time increases, as would be the case during a brake release. Timely release of the brakes is as important as the brake application itself. So a quick release valve is installed between the chamber and the brake to shorten the brake release time. A quick release valve, such as the QR1, has only one moving part, a diaphragm. Air from the brake valve enters the QR1 at the supply port during a brake application. Entering air causes the diaphragm to seal the exhaust port. It also bends the outer edge of the diaphragm away from the valve body, allowing air to flow to the chambers being served. When the brake valve enters the holding or balanced position, air pressure above and below the QR1 diaphragm is equal. The outer edge of the diaphragm will seal against the body. The exhaust port remains sealed. Like the brake valve, the QR1 is also now in the holding or balanced position. When the brake valve application is released, the air pressure above the diaphragm is released back through the brake valve exhaust port. Air pressure beneath the diaphragm lifts it, opening the exhaust of the quick release valve. This allows air in the chambers to exhaust at the QR1 rather than traveling back to the brake valve. The QR1, most often used on the front or steering axle brakes, speeds up their release. Because the driver and the brake valve are relatively close to the front brakes, the time to supply those brakes is very short. But the brakes farther away require help from a relay valve. Use of this valve on rear axle brakes, particularly on long wheelbase vehicles, assures simultaneous application of the front and rear brakes. A relay valve is usually installed on or near the axle or axles it serves, in this case, the rear axle. The valve requires a control or service connection to the delivery of the brake valve, a supply connection to the air reservoir, and delivery connections to the brake actuators. A relay valve speeds up the application and release of the brakes. It's essentially a remote-mounted, air-controlled brake valve. It applies or releases the brakes it is connected to in response to the control air from the foot valve. A typical and one of the most popular relay valves is the R12. It consists of a relay piston with an integral exhaust seat, the inlet and exhaust valve assembly, and various O-rings. With brake application, air pressure from the primary circuit of the foot valve travels to the relay valve control port, enters the small cavity above the piston, and causes the piston to move. As the piston moves, its exhaust seat contacts the exhaust portion of the inlet exhaust valve, sealing the previously open exhaust port. Continued movement of the piston unseats the inlet valve. This allows the supply air to flow from the reservoir past the open inlet valve and into the service portion of the spring brake actuator. When air pressure beneath the piston equals the service air pressure above the piston lifts slightly and the inlet valve spring returns the inlet valve to its seat. The exhaust remains closed. The relay valve is now in the holding or balanced position, and service line pressure is equal to the delivery pressure. The brake valve is also in the holding or balanced position. If air pressure above the piston is increased, as from a stronger brake application, the piston will again move in response to the added pressure, unseating the inlet valve. The inlet valve remains open until pressure beneath the piston equals pressure above the piston. Then the inlet closes and the R12 is returned to the balanced position. When the driver removes his foot from the brake, air above the relay piston returns to the foot valve and is exhausted to atmosphere. As air pressure above the relay piston decreases, the higher pressure beneath causes the piston to move away from the exhaust valve. This allows service brake air to return to the relay valve and flow out the open exhaust port. The brakes are now released. Here's service tip number 3. Always replace a relay valve with the same or similar valve. Most service relay valves, including the R12, incorporate a differential or crack pressure. It's the amount of control air pressure needed to open the inlet valve of the relay valve assembly. The crack pressure must stay within plus or minus 1 psi. The standard R12 has a 4 psi nominal crack pressure. That is, there will be about 4 psi above the relay piston at the instant the inlet valve opens. The R12 is available with crack pressures from the standard 4 psi up to 10 psi. Brake application timing can be affected with an incorrect relay valve. Now let's look at the last device needed in our basic service brake system, the stoplight switch, an air-operated on-off electrical switch. Generally, a switch is used in each of the service circuits. 2 are used in case of a failure in either brake circuit. The Bendix SL5 stoplight switch is comprised of a body, a non-removable, non-metallic cover, piston, diaphragm, 2 contact strips with attached terminals, and a shorting bar. During a brake application, air flowing to the brake actuators or relay valve also reaches the stoplight switch inlet. Air pressure is immediately present beneath the SL5's diaphragm. When application pressure reaches or exceeds 6 psi, the diaphragm moves, carrying the piston into contact with the shorting bar. With continued movement, the shorting bar snaps into contact with the terminals, completing the circuit and lighting the stoplights. Upon release of the brakes, air is exhausted from beneath the SL5 diaphragm, the shorting bar loses contact with the terminals, and the electrical circuit is broken. That completes the basic service brake system that will safely stop a vehicle in normal service. Let's take a moment to review. The E6 receives air pressure from the system's 2 circuits and applies or releases either the front or rear brakes, regardless of failure in either. The slack adjuster rotates the brake camshaft, causing the brake shoes to contact the drums. Drum-to-lining clearance is also adjusted. Quick-release valves ensure timely releases of the front or steering axle brakes. The R12 relay valve speeds up the actions of the rear brakes so the front and rear brakes apply simultaneously. Stoplights are lighted by the SL5 electrical components activated by air pressure. We hope your understanding of a simple service brake system and its components has been enhanced. For complete service and preventive maintenance information, obtain a copy of the complete Bendix Maintenance Manual at a local authorized Bendix parts outlet.